All right, this is Tuesday, December 8th, 2020, Physics CP. I'm going to be lecturing about circular motion, including how to calculate normal force in a rotational situation. All right, so to begin with, if I were to walk around in a circle, and at one moment I'm going at a speed, I don't know, let's say 2 meters per second. And then later on, when I'm a quarter of the way around the circle, I check my speed and I'm still going what I say? Forgot what I said already. So if I'm going 2 meters, a meter, 2 meters per second here, I'm going 2 meters per second here, halfway around, I'm still going 2 meters per second, 3/4 of the way around, I'm still going 2 meters per second. Yes, I can still teach. My question is, am I accelerating? Speculate, please. What do you think the answer might be, Joshua? That's a strange response. Why would you say that? Oh, okay. And Nathan M., do you agree? Nathan, yeah? No, Nathan M. M. The other one. Well, maybe the other one's not going to respond today. Oh, sorry. I'm doing the wrong uh, list. Let me try that one. Yeah, Nathan H., go ahead. Okay, so time for something educationally new. Velocity is a vector. And what that means, as a reminder, when I have a vector is a magnitude and a direction. That's what makes velocity different from speed. Speed, speed is a scalar, and that means magnitude only, no direction. So my slowest speed can be 0. Doesn't matter what direction I'm trying to move. Whereas my velocity can actually be a negative number if I define the direction that I'm moving as being a negative direction. So velocity is a vector. And at this moment, when I was on the circle, my speed was constant. And let's say I'm using a compass and I'm looking down from above the top of this thing. So towards the top of the sheet of paper represents east, to the right, I'm sorry, north, to the right is east, down to the bottom of the paper is south, to the left is west. So at this moment, I was heading north. Later, I was heading west. Later still, I was going south. Even later, heading east, and then repeating over and over again as I go around and around the circle at a constant speed. So the result is I am accelerating because my direction is changing. And so this raises a math question like, well, when I say I'm accelerating, just because I'm changing my direction, in what direction am I allegedly accelerating? Am I accelerating to the west? Am I accelerating to the south? Am I accelerating to the east? What direction am I accelerating? Good old Sir Isaac Newton tackled this problem. And so I'm going to do two snapshots. This circle is radius r. And anytime I'm moving around the circle at a constant speed, my speed is tangent to the circle. So that's really a right angle between my velocity and my radius. Now consider a short time later. I've moved through some angle, theta. My radius hasn't changed. The magnitude of my velocity hasn't changed. So if I could draw an arrow tangent, I would draw it the same length as this earlier one. And so what has changed between this initial moment, I'll call it sub I, and this later moment, I'll call it final sub f. Here I had initial velocity, here I have a final velocity. All of this is after a short interval of time, delta t. Delta from math class means change in time. Okay, so my sketching skills are terrible, but I'm going to make an attempt here at drawing the radius vector a short time later, same length, the angle theta, and the change from my initial position to my final position, I'll call that delta r, my change in position. So an arrow to the right, an arrow up and to the right, and a tiny arrow pointing from the tip of the first one to the tip of the second one. I do teach math in summer school, but right now I'm not going to prove it to you, but I will declare to you that if I draw the velocity vector the way it was at first, and then the way it was that same short time later, then the angle is going to be the same. If this thing changed by 10 degrees, then this direction also changed by 10 degrees. If this changed by 1 degree, this direction changed by 1 degree. So it's the same value of theta. And now I can draw from the initial to the final a little teeny tiny triangle change in velocity, delta v. My claim is not only are both of these isosceles triangles, which means they have the same lengths on two of their three sides, but because they also have the same angle, they are similar triangles. And you're wondering, well, that's fine. Why do I want to do anything with that? Because mathematically, here's what we're going to do. We're going to take the ratio of the little skinny side to either one of the long sides and make them similar to each other. So what does that mean? The ratio of delta r is to r as delta v is to v by similarity, right? Little change in r is to one side, as little change in velocity is to one side. So this is a perfectly legitimate mathematical expression. Now, I'm going to divide both sides by the change in time. So divide by delta t. Divide by delta t. You wonder, where am I going with this? Well, watch. Delta r divided by delta t divided by r on the left is equal to delta v divided by delta t divided by v on the right. Haha. And now, two little substitution tricks. First, I remind you that if we were going in a straight line, then your change in position is equal to your velocity times your change in time. This is what I used to call equation 0 when we studied the four kinematic equations of motion, because this one was for a situation where there was no acceleration going on. You were just moving in a straight line. And it says, in a straight line, the distance you travel is the product of your speed times time. For example, if I was walking at 2 meters per second and I walked for 5 seconds, then beep, 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 I walked 10 meters. 2 meters per second times 5 seconds is 10 meters. In a circle, we could talk about how the circumference is 2 pi r, but we're going to zoom in and look at just a brief portion of the circle. This is a distance here, delta r. And that distance, delta r, the distance that you move along the circumference of the circle, really, is the product of your speed times the amount of time you're moving at that speed. A little blurry. So I can substitute delta r divided by delta t is another way of expressing my speed v. I'm going to substitute for I'm going to substitute for delta r over delta t back over here. So instead of writing delta r over delta t, I can just write v divided by r. And that's going to be equal to delta v divided by delta t divided by v. All right, Dylan, glad you finally got here. Okay, records updated. And Daniel, you're still here. Well, wonders never cease. Okay, I have one more trick. And that trick is the definition of acceleration. Acceleration, A, is defined as the change in velocity divided by the change in time. So what the heck? I'm going to substitute for this back over here because this is where it shows up. Ah, yes. So now I have V divided by R is equal to A divided by V. These V's do not cancel. Instead, what I could choose to do is multiply both sides by v. What I have on one side is the acceleration, and I'm going to give it a little subscript, letter c. On the other side of the equal sign, I have v squared divided by r. This is a formula developed by Isaac Newton. He was born in the 1600s, and it's to calculate how much acceleration we're talking about when we're moving around in a circle. This C is short for the word centripetal. Centripetal means center seeking. Center seeking. Okay, imagine if I had a washer on a string and I start to twirl it around. The string is the radius. And I'm always pulling it towards the center of the circle. If I let go of it, then by Newton's first law, the washer will go flying off at a tangent to the circle. Newton's first law says an object at rest remains at rest unless a net external force acts on it. It also says an object in motion will continue in uniform motion. That means it will keep going in a straight line without changing speed or direction unless a net external force acts on it. So the washer is constantly trying to fly off at a tangent to the circle. The string is what's preventing it from doing that by constantly pulling it towards the center of the circle. The direction of this pulling is always towards the center of the circle. So that's how this got its name of centripetal acceleration. By the way, this explains why the moon goes around the Earth. If the Earth were the center of the circle, and I replace the washer with the moon, a quarter of a million miles away from us, it's the pull of Earth's gravity that is accelerating the moon towards the Earth. If we shut that gravity off, the moon would go flying off into space at a tangent to its orbit. But because of the pull of Earth's gravity, the direction that the moon is moving is constantly changing, constantly changing, constantly changing. And that's how it ends up orbiting the Earth. It's going about 1,000 meters per second in its speed, but it's accelerating towards the Earth, oh, I don't know, an inch or so per second, a couple of inches per second squared. It won't hit the Earth because it's going off to the side so fast that the Earth curves away underneath it before it gets to the surface of the Earth. All right, that seems like a lot to throw at you right away. Let's do maybe an example or two, I would say. Oh man, perhaps we just need someone to give us some numbers. Say Fabian, well, give me the radius of some random circle. All right, 7.5 meters. And I'm going to add a little zero. And at what speed is the object moving? Dylan M. 10 meters per second. All right, that is enough information right away that we can calculate how much an object moving at 10 meters per second around a circle that's about a little more than half the width of a classroom in radius. Okay, so this would not fit in our physical classroom at school. It had to be done outdoors. And this is moving faster than you can run. So I'm expecting a kind of large value for the acceleration. Calculate, please. What do you get for the acceleration in this example? Matthew. Nathan, do you agree? Nathan H. Okay. In other words, your acceleration would be even greater than the acceleration due to Earth's gravity. So if we had a little object there and I were pulling on it with a string, the tension in the string would be even greater than the weight of the object at the end of the string. So if I was pulling on a 1 kilogram mass that weighs 9.8 newtons, I would be tugging on it with a force of 13.3 newtons. That's because F equals ma. So a 1 kilogram mass that I have to accelerate at 13.3 meters per second squared would require a force, a pulling force, a tension of 13.3 newtons. All right, let's do another one. Suppose I have a space colony. I love these things. And it's in the shape of a huge donut. Okay, so do you want it to be a hollow donut or a filled donut, Sean? Okay, so when it's filled, the entire inside is enclosed and it rotates. This is called artificial gravity. As it rotates, you could stand against the outer wall. Here's your feet, your hands, there's your head. And it's the wall that is pushing against you to prevent you from going off at a tangent and instead move along in a circle. Meanwhile, a person on the other side of the space station would be standing against the wall over there. And as they look up, they would see the top of your head above them, just as you would see the top of their head above you. In the 1970s, NASA tried to design a space station where the acceleration would be 1g, 9.80 meters per second squared. And they were worried that people would get dizzy if it spun around too fast. So they made a guess that if it only went one revolution in a minute, then people would not get dizzy. In the 1990s, the Air Force actually did experiments and found out that, oh, you could actually spin 4 times in a minute and not get dizzy for most people. And then with training and conditioning, you could even spin more times in a minute. The faster you spin, the smaller the radius has to be. So let's pick a foolish number. Let's say I'm hoping to have a space station whose radius is, well, let's make it 225 meters. And by the way, this is huge. This radius is twice the dimension of the International Space Station. So we're talking about a huge thing. My question is, if this is the acceleration I want so that we have full Earth gravity, and today we don't even know if we really need full Earth gravity to be healthy. We've never done experiments other than at 0g. If I have a radius of 225 meters, what would be the speed at which I would be spinning around on the space station? Calculate, please, knowing that the acceleration is v squared divided by r. Solve for v and tell me what would be the speed at which you're spinning. Tyler, what do you get? Standing by. No units. No units? Oh, okay. So there you have the units. Yikes. Jacob, do you agree? Right. Because when it's 46.95742,753, you should round up, don't you see? All right. So the speed is 47.0 meters per second. And there's the timer telling us we can take, here we go. All right. Now, let's add to this a bit. You probably fully remember Newton's second law. Newton's second law says F equals ma. In the case of gravity, the force of gravity, which by the way is also the same thing as your weight, that's the product of your mass times the acceleration due to gravity. So that's how we calculate your weight, of course. And the force that goes here could be the force of gravity. Often it is the net force acting on you. But my claim is it can also be the centripetal force. which would be the product of the mass of the object times its centripetal acceleration, centripetal force. One thing that might not be too clear, and maybe I should back up a page that I just threw away, is the centripetal force is a calculation of what force is needed in order to cause the object to move in a circle. Okay, so think back to my first drawing. I said if I had a string with a washer at the end of the string, then I would have to pull on the string towards the center of the circle all the time. So it's telling me how much tension I would need to apply to the string for the result of having this washer move in a circle. If I don't supply the calculated tension, then this thing won't move in a circle. If I pull too hard, it'll, move into the circle. If I don't pull hard enough, it'll move out of the circle. So centripetal force is a calculation of how much force needs to be applied to get, as a result, uniform circular motion. So uniform means same speed. We're not speeding up or slowing down. I also talked about how if this were the Earth and that were the moon, it's the gravitational pull between the two of them that is supplying the centripetal force. So what should I call it in that situation? Should I call it the centripetal force or should I call it the gravitational force? Well, you can choose. The gravitational force is the centripetal force causing the moon and the Earth to actually orbit their common center of mass. So the Earth actually wobbles around a little bit as the moon orbits around it. And that little wobble, it doesn't even come outside the surface of the Earth. It's a small circle. All right, so for the space station, what is supplying the centripetal force for these two people who are on the inside of the space station? I see I'm using the wrong the wrong page. Okay, so this is the one I used today. And here's the drawing from today. I'm catching up to me. There's no gravity that's significant pulling you to the person on the other side. Instead, you're being pushed through your feet to change your direction. That's why you can walk along this wall. You can walk over to this person by just walking over here. And of course, if you were to run at the magic speed that the space station is spinning, why then you would be floating while the floor spins underneath you. Wouldn't that be interesting? So if you were in the middle of this thing, not spinning, you would see everything around you spinning away, and you would just be floating there, not spinning. The point I'm trying to make in terms of physics is that it's the wall pushing against you that provides the centripetal force that we need. And the force that is perpendicular to two solid surfaces in contact with each other is called the normal force. For a space station, the normal force provides the centripetal force that we need to continue moving in a circle instead of flying off at a tangent to the circle. Wonderful. Wonderful. Okay. So, armed with this deep understanding of centripetal force and how it's related to normal force, what if I took a ramp and at the bottom of this ramp, I built a little loop de loop? This used to be a toy that you could buy as a kid, probably less popular than electronic toys today. And we have a device that looks very much like this in the science building. And instead of racing cars down it, although I think we have those toys too, we can roll a marble down this thing. You might be starting to recognize that this looks an awful lot like the roller coaster homework assignment that you guys had to deal with earlier. Oh man, I happen to have that assignment. The second part of this assignment had a ramp that went to a loop de loop. And on this homework assignment, there were questions that asked, what is the normal force acting on the ball at point C? What is the normal force acting on the ball at point D? So today, I'm going to try to teach you how to correctly calculate those answers. But I'm not going to use the values from the homework assignment. Let's use a few different values instead. So I need a mass for this little marble. And random volunteer, what is the mass of this little marble? Tony. Okay, that's an actual true marble then, 12 grams. And I remind all of you interested students that 12 grams is 0.012 kilograms. Okay, because there's 1,000 grams in a kilogram, you move the decimal point 3 places to the left when converting from grams to kilograms. And I'm going to start this marble. I'll start it from rest. We'll keep this simple. From a height of how many meters, Jaden? Whoa, my goodness. That is a tall ramp, 32 meters. That's a 10-story building there. Wow, you built yourself one heck of a ramp. And by the way, they did build a ramp similar in height, but it didn't go to a loop de loop. It it was just a slide, and the bottom of the slide was water, a lake. I mean, it was a lake or a huge pond or a bay. And what you know people seeking fun would do is they would slide down this slide and then skip across the surface of the water 70, 100 feet, quite a distance. And so that was a fun activity. I suppose someone killed themselves. I don't know what happened, but they don't do such things today, probably because of safety concerns. This was done on the East Coast of the United States 100 years ago or so. All right. So we have a 32-meter high ramp, and I need a radius for this little loop to loop. Harshit, this is not to scale. What would you suggest as a radius for the loop to loop? 3. All right. The radius is 3 meters. And I think I'm going to have to reject that because that is too much like the homework problem. And we need other values. So, Jonathan, give me a replacement value. No, guys, no, nothing related to this. Uh, Off you go, Siddharth. Okay, 1.70 meters. What a big difference that is. Okay, so if I were to do this to scale, if this is 10, 20, 30 meters for the height, then 1.7 meters would be about this height for the diameter. Okay, so if this were the ramp, this would be the loop to scale. Not this at all. Okay, so we're really doing something like this, although my sketch looks like that. Great. We're going to use energy to figure a couple things out. First, how much total energy do we have in a situation like this? I remind you that we've got gravitational potential energy and possibly kinetic energy. The gravitational potential energy is m times g times h. The kinetic energy is 1/2 times m times v squared. We're starting from rest with a 12-gram marble at a height of 32 meters, presumably on planet Earth. What is our total energy, Ray? Reynaldo. I could not quite understand that. Child, I think you need to type in the chat and stop breathing helium. All right. And Zara, do you agree? Ouch. That hurts, kids. Because we don't use 12 grams, we use 0.012 kilograms. Oh, so therefore, Zara, the correct value would be what? Ray, how about you? Guys, oh man, Zara, do you agree with that? So I'm child, look. Did I use a calculator to go from here to there? No. So can you please not use a calculator to go from Ray's answer in the chat to the correct value, please? Well, that would move the decimal place once. But how many places did I move the decimal? Oh, that was painful. But yes, 3.76 joules is the energy of a 12-gram marble after it has fallen through a height of 32 meters. 3,000 joules would create a crater. Wow. Okay. So that would be dropping a massive bowling ball from the top of a 10-story building, if you want to try to imagine what would happen. All right. So we've got our 3.76 joules. And now that the radius is 1.7 meters, let's do the top in case I run out of time. At the very top, the centripetal force would have to be pointing down. In order to know what the centripetal force is, I need to know what the speed is. In order to know the speed, I need to know its kinetic energy. The total energy is 3.76 joules. What would be the kinetic energy at the top of a circle of radius 1.70 meters above ground level? Yikes. I think you understand what you need to calculate is how much gravitational potential energy you have at this new height. And, by the way, 1.7 times 2 means the height here is 3.4 meters above the ground. So we have that much less kinetic energy due to this increased height. Wow. Here, do this little calculation. If I were to height of 3.4 meters above the ground with a 12-gram marble, how much gravitational potential energy would that marble have? Okay, let's just do that calculation. I have a 12-gram marble, 3.4 meters above the ground. How much gravitational potential energy would that marble have? Tenrusi. Eric, do you agree? Oh, what do you get? Yes. Okay. So the numbers that we're plugging in for the mass, I'm going to use kilograms, 0.012 kilograms. For the acceleration, I'm going to say that we're on Earth, so times 9.80 meters per second squared. And for the height, it's going to be a diameter for a circle of radius 1.7 meters. 1.7 times 2 is 3.40 meters. So my calculator says 0.39984. So I'm going to call that 0.400 joules. To 3 sig figs, it's 0.400 joules. Okay? Now, if the total energy is 3.76 joules, and the gravitational potential energy at the top of this loop is 0.400 joules, how much kinetic energy does this marble have at the top of the loop? This is one you can do in your head without a calculator. Siddharth, what do you get? Tyler, you as well? Siddharth, why do you need a calculator for this one? Daniel, do you agree? Interesting. Interesting. Huh. If the total energy is 3.76 joules, and at a height of 3.4 meters, 0.40 joules of that is in the form of gravitational potential energy. That was weird. That was very weird. So I only have 3.36 joules of kinetic energy. Okay, now let's calculate the speed of that marble. The formula is 1/2 mv squared. Solve for the speed of the marble, knowing that it has 3.36 joules of kinetic energy and a mass of 12 grams. Joseph Q, what do you get? Jaden, do you agree? As do I. 23.7 meters per second. That means we can now calculate the centripetal force. Yeah, well, let's calculate the centripetal acceleration. The formula is v squared over r. Yikes. Tyler, what do you get for the centripetal acceleration? Okay. Mm, I don't think I'm going to edit out. Repeat that, please. Yeah. I only got 329, but okay. Meters per second squared, which is tremendous. Now, the centripetal force would be the mass of the marble times that acceleration. What is the centripetal force, Eric? Dylan, do you agree? Somehow, I'm not getting anything close to that. I have a mass of 0.012 kilograms, and I multiply that by 329 meters per second squared. So what do you get, Dylan? Okay, anyone, what do you get? All right, yes, 3.95 newtons is how much force would have to be applied in order to have the marble move in a circle. Now, not to scale, but the marble has a weight, and the weight of this marble is 0.12 kilograms times 9.8 meters per second squared. That is 0.12 newtons. Here's the point I'm trying to make. Because the weight is already pulling the marble down by that amount, the normal force is reduced by that amount. So the normal force in this situation is the 3.95 newtons that we need to make that marble continue to move in a circle, reduced by the weight of the marble of 0.12 newtons, because gravity is helping by that amount. So in this problem, the normal force is 3.83 newtons at the top of the loop. Oh man, the period's ending. I'm going to go over by a minute and tell you that at the bottom of the loop, you have to fight against gravity. And so you have to uh, increase this thing up to 4.07 newtons of normal force at the bottom of the loop. Okay, this ends our educational